Welcome to a lesson with Dr. Powell. Let's look at an example of diagonalizing a matrix and what it is. Essentially what we're doing is we're trying to multiply matrix A by matrix and its inverse to get a diagonal matrix. This is the same thing as writing the matrix A with respect to a basis determined by the columns of P. So we're sending like E1 to the first column, and then this acts on that, and then we send it back, and then we send okay, so A acts on that, and if it's an eigenspace, it'll act like a scalar on that, so it'll just be a multiple of that. So this will actually send us back to a multiple of that same standard basis vector, and that's why the diagonal matrix will really be diagonal. We're just going to be taking scalar multiples of standard basis vectors, kind of like this. Like E1 is sent to something, which is then the matrix just multiplies it by 4, and then that's just goes backwards to that. So we get a nice diagonal matrix here. So with respect, so if we change coordinate system to a skewed coordinate system, where the basis was actually the eigenvectors themselves, so they should be linearly independent for this to even work. Which goes back to we need our minimal polynomial. Actually, that in and of itself requires that our minimal polynomials can't have any factors of degree 2. Has to only be all degree 1 in our minimal polynomial, really, to allow that to happen for a basis. So we're just writing this in terms of another basis, so it looks like a diagonal matrix. So how do we do that? We take this, we find its characteristic polynomial by saying like x identity minus this, taking the determinant, looking at this, factoring it, getting our different degree 1 polynomials. That will be minimal polynomials on here. And this guy right here makes the range. So this guy, since this is a very simplistic situation, we can just look at the range of, we can look at the range of x minus 1, and x minus 4 is the minimal polynomial on that. These are both, dimension 1, so it fills out very nicely. So we can just do this quick. We look at the range of x minus 1 to get the eigenvector for the eigenvalue of x equals 4. So we just take this matrix, subtract 1 down the diagonals, get this one. And notice that both of these are multiples of that guy. So that's so what we can do in our P, we can write down -1, 1. In our diagonal matrix, we write a 4 here. Okay, and then here, x minus 1 makes the range of that 0. So then what we do is we compute the range of this by just taking this matrix and subtracting 4 down the diagonals, looking at this. Oh my goodness, that one right there looks like a -4, 1, and associated with the eigenvalue of 1 here. So then we have a 0, 0. There's our diagonal. There's our P. Then we just take the inverse of P, which we can do by swapping those entries, 1, -1, and just negating the things on the off diagonal. This is what we can do for 2 by 2s. Then we take its determinant, and we see that's -1 plus 4. So -1 plus 4, which would be 3. Let's make sure that's -1 and then plus 4, right? So 3. So then we just multiply that by a third. And there we have our diagonalization right there. Thanks for watching.